In this video, we're going to talk about the two-dimensional divergence theorem. Let's let our vector field F represent a fluid flow in 2D. And what we want to define is the flux of F across our curve C. So we could say that's the total outflow across C minus the total inflow across C. And that way we can rephrase that more quickly as the total net outflow across C. Now, if we want to come up with a mathematical definition for this flux, then we need to talk about the normal vector to a curve. So let's draw a picture. Let's say we've got a curve. We're in 2 dimensions, so this is just a curve in the xy plane. And specifically, we're going to let this vector little n here represent the outer unit normal vector to our curve C. So let's draw a picture here. So let's say we're at this point on the curve right here. So n is pointing out of the enclosed region. That's what makes it outer, pointing away from the enclosed region. It's unit, meaning it's 1 unit long, and it's normal to our curve, so perpendicular to our curve. So at this point, let's say outer unit normal vector might look like that, perpendicular to our curve. At this point, maybe it looks like that. So that's n at that point, n at that point, and n at that point. So at every point along the curve, you can think about drawing this outer unit normal vector to our curve. And with that, now we can write down a mathematical definition for the flux of F across our curve C. So we're going to call this the two-dimensional flux. I want to emphasize that it's in 2D because we will see 3-dimensional flux in a later video. And we're going to use the symbol capital Phi for flux. So there we go. So definition of 2D flux, it's going to be the line integral around C. Since C is a closed curve, we're going to write a closed line integral there. And what we're integrating, vector field dotted with our outer unit normal vector times ds. So beside this definition, I'm just going to write down our intuitive definition from above. So this is the total net outflow across C. So let's try to understand this definition using a picture. So here's our curve C. So let's say we're focusing on this point here. So at that point, we can draw our fluid flow vector, and we can also think about drawing our outer unit normal vector. So at that point, n might look like that. All right, now if we do the dot product of F with n, then what we're capturing is the component of F in the direction of n. So let's say F dot n might look something like that blue vector there. So just imagine resolving your vector F into components, one parallel to n and one perpendicular to n, and F dot n is giving you that component. Because if we think about this from linear algebra, F dot n is the length of F times the length of n times cos theta, where theta is just the angle between those two vectors. And since n is a unit vector, that just becomes length of F times cos theta, which is just your component of F in the direction of n. So more intuitively, we could say F dot n is the magnitude of F in the direction that's perpendicular to C. Now let's bring ds into the discussion. So I'll draw another version of this curve here. Here's our curve. ds, just a little chunk of arc length. So then what phi does is it takes an infinite sum of expressions that look like this, F dot n ds, and it's doing that sum over infinitely many tiny little chunks ds. So these little chunks ds just being little chunks of the arc length around our curve. So this quantity is giving us the net outflow across the curve in this little neighborhood here. And as we sum these up over these infinitely many tiny little chunks, then we're getting our total net outflow across our curve. So at points where F is pointing out of the region, you're getting a positive contribution to the outflow. And then you may have some points where, say, F is pointing into the region like that, and then you'll have a negative contribution to your outflow. So our vector n would be pointing like that. And then when we take the dot product of these two vectors that have greater than 90 degrees between them, we're getting a negative value for that dot product. So negative contribution to that sum. And therefore, we're getting our total net outflow across our curve. So what we have at the top of the screen here is a definition of what flux is. But to actually compute flux, or if we wanted to calculate it in a specific example, we would use a different formula. So let's talk about how to calculate flux. To calculate flux, we're going to look at what's called the two-dimensional divergence theorem. This is also called the vector form of Green's theorem. So one theorem just has two different names. So the theorem says, let C be a simple, closed, positively oriented curve that bounds a region R. Okay, so we're in 2D, we've got this curve here. It's got no loops in it. The start point is equal to the end point, and it's positively oriented, so we're keeping the region R on our left as we travel around C. So same setup as we had for Green's theorem and for the corollary to Green's theorem. So here's what our 2D divergence theorem says. It says if you want to actually calculate flux, which is the closed line integral around C of f.n ds, then the way you actually calculate it is by doing a certain double integral over your region R. Put our dA at the back, and what we're integrating is the divergence of f, hence the name 2D divergence theorem. So in order to be clear on what the theorem is saying or exactly how it's helping us, if you like, you could actually just cross out this left side and just write the symbol capital phi there, or just write flux in words so that we're clear. The way that we're using this is to actually calculate the flux. So if you rephrase this in a more geometric way, then you'd be saying, well, flux is a certain infinite sum. What we're summing quantities like divergence of our vector field times dA. This is an infinite sum. We're summing over infinitely many of these tiny rectangles dA. So let's draw a picture of what that would look like. So here's our curve C. Our region R is in the interior. Imagine breaking that region up into infinitely many little rectangles, etc. And for each of these little rectangles, what we're computing is the divergence, which is a measure of the outflow at that point. So divergence is going to be positive if you got a lot of outflow at a point. It's going to be negative if you got a lot of inflow at that point. So you're taking that divergence, multiplying it by dA, which is the area of that little rectangle, and then summing those quantities up over all these rectangles in the region. So the idea is that there's going to be lots of cancellation in the interior. And physically, why there's a lot of cancellation is because if you have a big outflow at this point here, and then you look at a neighboring point, that neighboring point is then going to have inflow, because outflow from one point is going to count as inflow to a neighboring point. So in that sense, there's going to be lots of cancellation in the interior as you start to pack all these little infinitely many rectangles into that region. So what that leaves us with is a net effect on the exterior of the region. And when we say the exterior of the region, we just mean on the curve C. Now, to be sure that that net effect on our curve C is actually the flux, I would suggest we just do a units analysis here, talk about the units for the flux, units for divergence and dA, and we should convince ourselves that this net effect really is the flux of our vector field or our fluid flow across C. So let's talk units. We'll first talk about the units of our vector field. So we said in this context, we're imagining that our vector field is a fluid flow. And when we talk fluid flow, we do that as density times a velocity. And we're doing this in 2D. So our density is, well, for density, kilograms per meter squared times velocity, meters per second. So that would give us units of kilogram per meter second. And I think just to make this discussion totally clear, I want to write down the formula again for what we're comparing units for so that we can see that in front of us. So we're talking flux, which is the line integral around C of f.n ds. And we're saying that's the double integral over our region of divergence of our vector field times dA. Okay, so we want to work through units for, let's say, this specific equation. Okay, our outer unit normal vector n is unitless, and then we can talk units of ds. That's a little chunk of arc length, so its units are going to be meters. And then moving over to the right side, divergence of f. Well, the way that we get the divergence of f is by taking partial derivatives of our vector field with respect to coordinates like x or y. So taking that partial derivative is just going to introduce an extra factor of meters in the denominator. So if we look back at units of f here and just further divide that by meters, we would have kilograms per meter squared second. And then continuing with our units on the right side here, units of dA is going to be meters squared. All right, so on the right side, the total units that we're getting, we're multiplying units for divergence times the units for dA. So multiplying those together, we would have kilograms per second. So let's talk units for flux, kilograms per second, and let's confirm that's consistent with what we're seeing on the left side. So units for F would be kilogram per meter second. That's multiplied by units for ds, multiplying by meters. Yeah, sure enough, we have kilograms per second. So when we talk about our flux of F across our curve, if our vector field represents a fluid flow, then the units in which we're measuring that kilograms per second. And that shows in our previous picture that when we said there was lots of cancellation in the interior, and that was leaving us with a net effect on C, we now know that that net effect is actually the flux of F across C because it has the proper units, kilograms per second. So that's a physical justification for this 2D divergence theorem, also known as the vector form of Green's theorem. Bottom line, if we want to actually compute a flux, we're doing double integral over our region R, what we're integrating, divergence of our vector field. So let's try an example. So we are going to calculate the flux of the following two-dimensional vector field across the curve C, and we've got a visual description here of what this curve C is. So it's a semicircle of radius 4. It's the lower semicircle centered at the origin, and it's positively oriented. So it meets the assumptions of the 2D divergence theorem. It is a simple curve, it's closed, and it's positively oriented in that this region R stays on the left as we travel around C. All right, so let's break out the 2D divergence theorem that says if you want to calculate flux, then what you're going to do is a double integral over the region R, and what you're integrating is the divergence of F. So let's start by calculating the divergence of F. Flashback to when we talked about divergence a little earlier in this video series. So by definition, divergence of a vector field means take the partial with respect to x of your first component, and then add on the partial with respect to y of your second component. So let's try that. So partial with respect to x of the first component is going to be 8y squared minus 7. And then to that, we're going to add the partial with respect to y of our second component. So that's going to be 8x squared plus 7. And if we simplify that, that's 8 times x squared plus y squared. Okay, so that's going to be our integrand for this problem. Then just like with any double integration, we can think about how we want to set up our double integral. So we could use vertical slices or horizontal slices or convert to another coordinate system. But I would say in this example, because we're dealing with a semicircle, polar is going to be the easiest way to go. So we're going to switch this over to polar coordinates, and we're going to call that 8r squared when we switch over to polar. Now the other thing we need to do is come up with a description for our region R. So in other words, we need to find our limits of integration. So maybe I'll just do that over on the side here where we can still see our picture. So this semicircle here has radius 4. If we were to sweep through this region here, with just these rays going out from the origin like that, we would want to capture all the radius values between 0 and 4, and the angles that we would want to capture would be from pi to 2 pi, just to capture the lower portion of that circle. And if we are moving over to polar, then our dA is going to become r dr d theta, because remember there's that correction factor when we move from rectangular to polar. So with that, I think we're ready to set up the double integral for our flux. So I'll just recopy what we said from above. According to the 2D divergence theorem, flux is going to be the double integral over a region of divergence of f. So let's plug everything in here. So divergence of f we decided was going to be 8r squared. dA in polar is going to be r dr d theta, and then we can put our limits of integration on there as well. So the r values are going to be going from 0 to 4 as theta goes from 0 pi to 2 pi. And then we could just clean up our integrand a little bit here. Let's multiply that together to call that 8r cubed. And then we're good to go with our integration. So we'll keep our outside integral on here, keep our d theta on there. Integrating 8r cubed with respect to r, we're going to get 2r to the 4th. And that needs to be evaluated at r equal 4 and r equals 0. So we're getting 2 times 4 to the 4th minus 0. And that's a constant times the integral from pi to 2 pi d theta. Integrating this part, anytime you integrate a differential, you're just getting the length of that interval that you're integrating over. So that's just going to give us pi for the value of that integral. So in other words, 512 pi is our answer. So let's look back at the question for a second. We're calculating the flux of this vector field across C. We don't know for sure from the context that this is a fluid flow, but that's the typical sort of context that you would be doing this in. So if F were a fluid flow, then this flux phi would be in kilograms per second. So you'd have 512 pi kilograms per second as your rate at which mass is flowing out across C. So we practiced the 2D divergence theorem, and therefore we now know how to calculate two-dimensional flux. Thanks for watching.